or grad phi dot n is 0. We cannot impose a no slip condition on ideal flows because no slip condition is not satisfied for outer solutions. The wall boundary condition is not satisfied for outer solutions. We'll have to zoom in close to the wall or surface, which whatever you want to call it. We'll have to zoom in very close to here. We'll have to zoom in inside a layer like this for being able to implement this no slip boundary condition, okay, which is what we saw from our basic ODE example, that u equals 0 couldn't be satisfied by the outer solution because we obtained all of these equations when we naively dropped the viscous terms. Okay, it is the viscosity which supports that no slip condition. You just dropped the no slip condition because you dropped the viscous terms from your governing equations. So we had looked at this ideal flow in a wedge. Just a basic recap for your from your introductory fluid mechanics class. So if you recall, then for a uniform flow, let us say uniform flow which is oriented in x direction, your velocity potential is simply, so if the speed is u naught, velocity potential is simply u naught x. Okay, then you may remember something like a doublet where this was, let's say there is a source here of strength plus q and a source here of strength minus q. So this is a source, this is a sink, and they are separated by this distance 2 epsilon. Okay, and then you can formulate the velocity, you can formulate the velocity potential for this guy as u infinity, or let's write it like some mu cos theta over small r. Okay, where this mu is the source strength, or sorry, the doublet strength. Okay, and this is basically obtained by, so mu is actually obtained by, as a product of this q times epsilon, and you take limit epsilon goes to 0 and limit q tends to infinity such that their product remains a finite quantity. So basically you bring infinitely strong sources and sinks very close to each other, but not on top of each other, because if you have them on top of each other then there's no flow. One is a source, one is a sink, there's no flow. If they are on top of each other exactly, you're evaluating these things in the limit epsilon goes to 0 and q such that q times epsilon is some finite quantity. So I don't know if you guys, I think this was covered in your basic fluid mechanics course, I hope. Huh? APL 106 or the equivalent in mechanical, this was covered, right? Yes or no? Yes, this was covered. You don't no, or you don't remember? Huh? No, that's not my problem, but this was covered, right? Okay. So if you don't remember, you can look in the textbook or you can look in the notes. So in the notes, actually what I am doing is, instead of doing these in the 2D plane, so these were done in 2D plane for you guys, I have derived the expressions for 3-dimensional versions of this. So you can do the uniform flow which remains as it is, and I have derived these doublet flows, and then you can combine uniform flow plus doublet. You can combine uniform flow plus doublet to model flow past a cylinder, or technically not any flow past a cylinder, ideal flow past a cylinder. So if this cylinder has a radius r, then you can write the combination of these two as the velocity potential. So u infinity x plus u infinity r square cos theta over small r. Okay, and where, so this x you can write as r cos theta in the cylindrical coordinates. Okay, so basically it's a summation of this guy and this guy. Okay, and the streamlines look something like this in a potential flow. So if you don't remember, then I suggest you look at your introductory fluid mechanics Frank M. White textbook or Fox and McDonald, whichever one was followed, and you find these expressions there. Okay. Of course, nobody is expecting you to remember, but these things should be fairly intuitive to you by now, because this is flow past a cylinder in 2D, an inviscid flow past a cylinder in 2D. A fourth year mechanics or a mechanical student is supposed to know this. Okay. So, this is something that you should know, and this is how the streamlines look like. What I am interested in showing to you is that the streamlines at least in 2D flows. So, in 2D flows where you can define a stream function such that del psi by del y is u and minus del psi by del psi del x is v. What you can show is that if you have these lines of constant stream function, okay, then these are actually the streamlines. So, in 2D flows, when you can define this psi, you can define this psi in axisymmetric spherical flows also, which you can take a look at in the notes. In if you can define this psi, the constant of this psi are actually the streamlines. How do we show that? So, along this line, if you say that I consider d psi, which is nothing but del psi by del x dx plus del psi by del y dy, and you say this is 0. So, this means dy by dx is actually equal to minus del psi by del x by del psi by del y, which from the definition is basically v by u. This means these are curves which have tangents to velocity. Okay, the tangents to these curves are basically velocity vectors. Okay, dy by dx is v by u. So, these are curves which have tangent and that is oriented along the velocity vector. This will be v, this will be u, right? So, that means the curve that that on which d psi is 0, these are actually the streamlines. This was the definition of streamlines, remember, curves which are tangential to velocity always, velocity vector. Okay, and now for a moment let us consider the curves which have this velocity potential as 0. So, on those curves you will have d phi, which is del phi over del x dx plus del phi over del y dy, and that guy will be 0. That means on those curves you will have dy by dx as minus del phi by del x by del phi by del y, which by definition is minus u by v. At a given point where these two curves intersect, the velocity vector is unique. So, at a given point where these two curves intersect, the slope, the product of slope is equal to minus 1, which means what? They are perpendicular. So, actually in 2D flows, this is how phi equal constant contours will look like. Okay. And you can think about, so if these are the streamlines, these are basically psi equal to 0 contours. Okay. These are psi equal to constant contours, basically not psi equal to 0, psi equal to constant contours, and you can draw locally perpendicular curves. You can draw locally perpendicular curves, and these are the curves of phi. Okay, here phi is constant on these curves, and this is actually very useful. This is useful in, if you think about what's going on here, if you look at, you are basically discretizing your domain or discretizing your space. You are dividing your space into these quadrilaterals. If you assume that locally these are straight lines, you are discretizing your domain in these quadrilaterals. Okay. So, this fact of phi and psi lines being perpendicular to each other is used in CFD to make meshes, which are not too bad of meshes. Okay. These are first approximation, even though you are interested in, let us say, a full solution, viscous solution, and not just ideal flow solution. But if you can calculate the ideal flow solution quickly, you can make a very nice mesh around the body, and then you can do your CFD and resolve all the boundary layers and so on. Okay. So, this is one basic concept that I wanted to highlight. Okay. And then after this, you had doublet. So, you have this flow past a cylinder, which is doublet plus uniform flow. Then you can also have a doublet plus a uniform flow plus an ideal vortex. Okay. And if you go to your introductory fluid mechanics textbooks, you will see that this guy, so this is ideal vortex. Okay. So, this basically models flow past a rotating cylinder. So, you have a cylinder that is rotating and you can compute the streamlines in that flow, ideal flow. Okay. All of this applies to ideal flows. And then the point here to make, if you again go back to your introductory class, introductory fluid mechanics course, you will see that there is a lift force which is generated, on a rotating cylinder, and that is equal to minus rho u infinity times gamma. Okay. And this you can relate it to the Magnus effect, which you guys have learned very qualitatively in your high school or whatever. So, lift force which is generated, where this gamma is basically the circulation strength of this ideal vortex. Okay. It is the circulation strength of the ideal vortex. So, for an ideal vortex, your phi is given by gamma theta over 2 pi. So, u r, which is del phi by del r, is basically 0, and u theta, which is 1 by r del phi over del theta, is gamma over 2 pi r. So, you have purely tangential circular streamlines in an ideal vortex. It is an ideal vortex, it is a vortex, but still the flow is irrotational. The flow is irrotational, meaning that you have these tangential velocity profiles. Okay. You have these tangential velocity profiles, but if you compute the vorticity, it will be 0 except for a point which is the center of this ideal vortex. So, ideal vortex is like concentration of vorticity on one point. At that point, your vorticity is basically tending to infinity, and at rest of all other points your vorticity is 0, which is why we call it an ideal vortex. The flow is rotational except for a point. Okay, the flow is rotational throughout the space except for a point, and it is a it's vertical motion, but the vorticity is 0. Okay, and you can compute this. So, you can compute this lift force. If you have this phi, using this phi you can compute the pressure distribution on this cylinder and compute this lift force. Okay, I will not go into the details of this, but what I will go into details will be that this concept is actually used for modeling flow past airfoils. So, you can look at the mathematical details of this in the notes. I cannot cover this because you guys are not familiar with complex calculus, but I can give you a basic brief motivation of this, and that is, if you can solve for this ideal flow past a cylinder, let us say, which is not even rotating, you can in a way transform this as flow past an airfoil. Okay, you can transform this as flow past an airfoil. Okay, and of course we know that flow past an airfoil is tremendously useful, practical. It is used for all your aerodynamic designs, and if you think about it, none of your planes were built in an era when CFD was available. So, most of the planes that you are flying in, they were designed by approximate theories like ideal flow analysis, and after that adding some viscous corrections. Okay, and this is exactly what was used in all of your aerodynamic designs, even during World War II and pre-World War II. Of course, there are viscous corrections that need to be added, but this doesn't give you a too bad of a analysis. Why? Because actually through this analysis you can compute what is the lift on your airfoil. You can get a very good estimate of the lift. What is missing in your ideal flow analysis is the drag. Okay, the drag that is, so drag on the sphere or a cylinder is actually 0 here. Drag force on a cylinder, if you have ideal flow analysis, is 0. But we all know that if you have a cylinder in a flow, it will experience some drag. Okay, so the ideal flows actually give a terrible approximation of drag. So the drag on an airfoil, you will get some very unphysical values, or let's say incomplete values, or very small drag you will obtain from ideal flow analysis, but in reality your drag will be large because of viscous effects. Okay, but lift forces can actually be very well approximated using ideal flow analysis. And so if you don't care about putting a big enough engine in your airplane, if you can always put a big enough engine in your airplane, you are always bothered about, can I generate a lift which is equal to the weight or more than the weight, then you can basically design an airplane with your ideal flow analysis. You don't really need any viscous analysis because ideal flow analysis gives you a good approximation of the lift. Okay. Now, I want to make a note here that probably in your high school you were given some weird type of a explanation that why does a shape like this, okay, let's say this is your airfoil, this is an asymmetric airfoil, why does an asymmetric airfoil like this generate a lift? Okay, probably you were given a very crude type of a reasoning that, oh, this is longer, this is shorter, so the flow at top is faster and stuff like that, the pressure is slower. The real reason why you have lift that is generated by an airfoil is actually that there is a net circulation. Okay, if you enclose a curve around an airfoil, you will see that there is a net circulation that is generated around the airfoil. Okay, and this circulation is actually completely opposite to the circulation that is generated in the trailing wake of the airfoil, because this, if you are considering everything to be an ideal flow, the net circulation has to be 0. Okay, so you do get some trailing vortex. This is called, let us say this is called a trailing vortex or a wake region or a wake vortex of the airfoil. Okay, you do get a circulation like this, and so you do get a circulation like this, and from this type of a circulation you can argue why there would be a lift. Now, why is this circulation generated? Some of you may say, oh yeah, but this circulation kind of represents intuitively that the flow here is faster, flow here is slower, right? Yeah, but that is not the reason. There's no causality here. The pressure and velocity occur simultaneously. It's not like velocity is faster, so pressure is lower. That is happening. Okay. So what happens is that there is a circulation generated around this airfoil, and that causes the lift. Okay. How is this circulation generated? You can basically solve this flow past an airfoil, ideal flow past an airfoil, and convince yourself that around a closed path you will see a circulation. Okay, you will see a circulation, and the lift on this airfoil will actually be proportional to that circulation, which is this minus rho u infinity gamma. Okay, whatever lift you generate, you will see that the circulation or lift force is proportional to that circulation. But unfortunately, this requires complex analysis, complex calculus. So I am going to skip this discussion in the class, but if you are interested, you can take a look at it in the notes. The only reason why I'm skipping is because unfortunately you guys don't know complex calculus. Okay. Now, we are not going to look at flow past airfoils in this course because we cannot do details of complex calculus, but what we can do is something that can help us approximate or at least give us a reason why there is no drag. Why is there no drag in an ideal flow? Even though viscous effects are 0, but you would expect that pressure gives us a drag. Okay, there will be some values of drag, but the drag is actually poorly approximated in your ideal flows. Why is that the case? So to that end, we look at an ideal flow past a wavy wall. Okay, the reason why I'm looking at a wavy wall is because, so let us say you have a wall like this and you have a free stream velocity u infinity grazing past this wavy wall. The reason why I'm doing it like this is because if I give you flow past some arbitrary shape like this, okay, you can basically decompose this shape into sines and cosines using Fourier transform. Okay, and if you know flow past one of those sines and cosines, since all of this analysis is linear, you can basically add the velocity potentials and obtain a flow past this kind of a shape. And if you know flow past this kind of a shape, you can basically extend it to y less than 0 and obtain a flow past this type of a symmetric airfoil, let us say. Okay, so this is like a building block for an analysis which gives you a result for this. Okay, that is why I'm looking at flow past this wavy wall. Okay, so of course all of this we are looking at in 2D. The governing equation is del square phi equal to 0. Okay, and this wavy wall is defined by y equals epsilon L sine kx, or let's call it alpha x. Okay, and I'm not taking very large waviness in the wall. I'm just saying that the waviness is much very small. So y, this epsilon is much less than 1, and this L is some length scale, some length. Okay, just so that this epsilon is a dimensionless quantity. Okay, so we are basically going to solve this equation. I am taking a wavy wall that is infinite in x. So that means x is your homogeneous direction. So homogeneous direction means that I can write this phi as some phi hat y e to the power I k x. I can basically solve for a particular complex exponential coefficient here and say that okay, this is my solution for a particular k. I can combine this solution for multiple k's and obtain a solution for this. Okay. So I can write my phi like this, and from here, or you could have reasoned it from your separation of variables argument, either one works fine. If you can identify a homogeneous direction, you can always put a perturbation in phi like this. Okay. Basically, our velocity potential is something like this. You have a u infinity x plus some epsilon phi prime. Okay. If the wall was not wavy, then this will be our velocity potential. I am saying that there is some phi prime correction that is added due to waviness of the wall. Okay. And then since del square phi is 0, which is equal to del epsilon times del square phi prime. So that means del square phi prime is also 0, and it's the phi prime that I am expressing as phi hat y e to the power I k x. Once you identify a homogeneous direction, you can always break down your perturbations like this. This will be useful again when we discuss instability. Okay, if you can identify a homogeneous direction for your undisturbed flow. So disturbance here means that waviness in the wall, if it is not there, let us say it is a flat wall, then this is your undisturbed flow. The flow in that case is uniform in x. So if you can identify this uniform direction or homogeneous direction in your undisturbed flow, then you can always break down your perturbation like this. And so breaking it down, substituting in the governing equation, we get minus k square phi hat plus d2 phi hat over dy square equals 0. So that means phi hat is some a e to the power ky plus b e to the power minus ky. Okay. Now obviously we want phi hat to be finite as we move to y tends to infinity. Y tends to infinity, phi hat and all the velocities etc. should be finite. So that means a is 0. So phi hat is some b e to the power minus ky. Now to solve for this b and what this k is, we need to apply boundary conditions. And what are the boundary conditions which ideal flows can support? Basically, if this is your n vector, then u dot n is 0 at the boundary or at y equals epsilon L sine alpha x. U dot n is 0. So at y equals epsilon L sine alpha x, we are saying u dot n is 0. So u is basically grad phi, where phi is this guy. So it is u infinity plus epsilon del phi prime by del x I cap plus epsilon del phi prime by del y j cap. What is n hat? How can I get n hat? How can I get the wall normal? If I know the wall equation, the curve, how can I get the normal? Gradient of what? So we have to write the implicit equation for this curve. So that is f, let's say f sum f is y minus epsilon L sine alpha x equals constant, is the equation defining this curve. So n hat is grad f by mod grad f, which is j cap minus epsilon alpha L cos alpha x I cap over the magnitude of this. I am not going to write it in detail as of now. So we are saying that u dot n equals 0 at y equals epsilon L sine alpha x. So what is u dot n? Take the dot product. What do we get? We get minus epsilon alpha L cos alpha x u infinity plus epsilon del phi prime by del y plus order epsilon squared terms, and of course divide by mod grad f equals 0. Okay. So from here we say that epsilon alpha L u infinity cos alpha x equals epsilon del phi prime by del y plus order epsilon squared terms at y equals epsilon L sine alpha x. Then what we do is we apply a Taylor series approximation here and say that this guy at y equals 0. So this guy does not change with y. Okay. This is same as at y equal to 0. There is no variation, there is no function of y here. Okay. There is no function of y here. This is, so we apply the Taylor series here. This is del phi prime by del y at y equal to 0 plus del 2 phi prime by del y square at y equal to 0 times an epsilon L sine alpha x plus so on. And now you see that this higher order term, due to this y being slightly different from y equal to 0, is actually an order epsilon squared term. Okay. So at leading order, at leading order, you can basically write epsilon alpha L u infinity cos alpha x equals epsilon del phi prime by del y at y equal to 0 only. You do not even need to substitute this complex y equal to epsilon L sin alpha x, because that is also an order epsilon quantity. So, the moment you substitute it in this Taylor expansion, you get an order epsilon squared term. And from here we get u infinity alpha L cos alpha x equals del phi prime by del y at y equal to 0. What was phi prime? So, phi hat was this. So, phi prime was b e to the power minus k y e to the power I k x. So, del phi prime by del y is minus b times k e to the power minus k y e to the power I k x at y equal to 0. Okay. Now, technically P prime is the real part of this, right. Technically phi prime is the real part. The velocity potential is not a complex, there is no complex quantity in actual governing equations. We introduce this e to the power I k x just to make our analysis simple. This is technically real part of this. Okay. I can write this real part how? So, this guy is basically real part of this. How can I write the real part? So, real part of b e to the power minus k y I can write as, so I can write the real part of this, assuming b is real, huh? Yeah, okay. So, assuming b is real, we can say b e to the, b k e to the power minus k y, it is simply cos k x. Okay. If you assume b as some complex, you will get some other quantity here. Eventually, you will get the same solution as we are going to just obtain in a moment, and that is, so remember this is at y equal to 0, it is equal to u infinity alpha L cos alpha x. So, substitute y equal to 0, we get b times k cos k x is u infinity alpha L cos alpha x. This means k is equal to alpha and b times alpha is u infinity alpha L. So, b is simply u infinity L, which coincides with this. Okay. If our assumption would have been wrong, then this would have been contradictory. Okay. And then we would have said, oh, you cannot just proceed by assuming b is real, b cannot be real, and so assume b some complex and then move forward. But we can assume b is real, because assuming b real, we get a real value of b. There is no contradiction here. So, we get the full solution as phi prime is simply u infinity L e to the power minus k y cos k x. So, of course, your total velocity potential, which is u infinity x plus epsilon u infinity L e to the power minus k y cos k x, is correct up to leading order. There are order epsilon squared terms which we have ignored in our analysis. Okay. So, you have to always write, it is always good to write this order epsilon square here to remind yourself that this is a leading order solution that you have found, it is not the full solution that you have found. And so, what is your u velocity, x velocity? It is simply u infinity, and then differentiate this in x, you will get minus epsilon u infinity. So, this should have been alpha y, right, and alpha x, because alpha is the known quantity. So, u infinity alpha L e to the power minus alpha y sine alpha x plus order epsilon squared. Did I miss something? I think there is a minus sign that I missed here, right? There is a minus sign here because of derivative in y. So this should have been a minus here. So b should have been minus of u infinity. And so, yeah. And from here, you can actually get a fairly good intuition of what is going on in the flow. What is happening is that the flow has a u infinity x direction velocity at y equal to 0. Okay, at y equal to 0, it has some u infinity direct velocity, and also if you put x equal to 0, and then after that basically the flow changes velocity as you move up and down on this wavy wall. As you move up, the flow accelerates and it has a maximum of velocity when this alpha x is pi by 2. It has a maximum x direction velocity here, and then it goes down, and then it has minimum velocity in the x direction at the crest or trough, sorry, and then it has a maximum velocity, it has a minimum velocity, and so on and so forth. Okay, and you can look at what is happening with your y direction velocity also. So v is del phi by del y, so this guy is 0, and you get epsilon u infinity alpha l e to the power minus alpha y cos alpha x. So this y direction velocity is actually at a 90-degree phase shift from your x direction velocity. So it is maximum here, which makes sense. Maximum in the negative direction, it will be here. At the maxima, it is 0, v is 0. It is maximum here in the negative y direction, it is maximum here in the positive y direction, and so on and so forth. Okay. Now from here, we can also formulate the stream function. We can look at how the stream function looks like. So stream function is basically, if you write u is, or let us say v is minus del psi by del x, then you can integrate this. Okay, you can integrate this in x and you can get the stream function. Okay, and there will be a constant of integration plus the stream function will be simply epsilon u infinity. So you integrate this cos alpha x. So let us say sine alpha x epsilon u infinity l e to the power minus alpha y. So if you have v as that, your stream function, so there will be a minus sign. So minus epsilon u infinity l sine alpha x e to the power minus alpha y plus some arbitrary constant. Okay, and from here you will see that your stream function basically at y equal to 0, it will resemble the wall surface, and as you move away from the wall surface, the stream function basically slowly flattens out. And at y tends to infinity, the stream function will be simply a straight line. You can also calculate pressure at y equal to epsilon sine alpha x, or by linearizing in this fashion, you can solve it at y equal to 0. You can get the pressure from your Bernoulli equation. Let us say your, so this is an ideal flow, you can apply Bernoulli equation across any 2 points. So let us say the pressure of the free stream is some p infinity. So you can say it is p infinity plus u infinity square by 2. And so you can use this to solve for pressure and use that pressure to compute any force on this wavy wall, and what you would discover is that there is no force on the wavy wall, which is of course not true from your practical experience or intuition. If you have some non-flat wall, there will be some drag force and everything. Okay, and the reason why we don't have a drag force is because we have basically ignored any viscosity in our analysis. Okay. We have basically ignored any viscosity in our analysis. So there are further discussions which are possible with ideal flows. For example, the discussion that we unfortunately could not do of flow past airfoils. Okay, that is actually very useful because you can design airfoils and you can do an analysis of flow past airfoils and at least predict the lift in flow past airfoils very to a very good estimate, to very good accuracy using inviscid analysis or ideal flow analysis. And then there are further discussions to three-dimensional airfoils. For example, let's say in a two-dimensional airfoil, we said that there is a circulation that is generated. So if you have a flow past a 2D airfoil, there is a circulation that is generated in this direction at the in the wake. So there is an opposite circulation that is generated in this direction. Now if you take 3D airfoils, which are basically actual wings, okay, then what we see is actually this is true. So there is some circulation or vorticity that is generated in the wake of these 3D wings. Okay, there is a vorticity that is generated in the wake of these 3D wings because the pressure at the top surface is actually lower than the bottom surface. But due to that pressure being due to there being a pressure differential, you actually have a circulation of flow from the tip of these wings also. So what is happening is that fluid is seeing this low to high pressure or high to low pressure zone at the wing tips. So let's say this is your wing and this is how it is going up going forward, and this is your tip of the wing. So there is a pressure that is higher on the bottom surface than the upper surface. So the flow actually turns from the tips in this direction, and these are what you usually call as wing tip vortices. So if you see, let us say some smoke and then there is a airfoil that is or there is an airplane that is coming through that smoke, you will see at the tip of the wing airplanes there are these vortices that are generated, okay, at the tip of the wing. So these are basically you see, and these are actually the reason of any turbulence that the wing leaves behind, an airplane leaves behind in its wake. Apart from a lot of other things, there are jet coming from the engine and so forth, but these things also, let's say if there is a glider which doesn't have any engine in it, then this will be a major source of turbulence behind that glider. Okay, and you can actually do a analysis of the lift generated by these finite wings. For example, let us say it's finite in both directions, then you will say that there are wings, there are vortices on this side of the tip, and actually what happens is that these vortices they end up merging with this line. Okay, they end up merging with this line. So there is a constant, there is a circulation curve that you can trace across a wing, and using that you can estimate the lift that is generated by this wing. Okay, so these type of all of these type of analysis can be done if you know how to do analysis of this. If you know how to solve 2D airfoils, you can do quite a lot of aerodynamic design for finite wings. Okay. Any questions? So, with this we will close our discussion of ideal flows, okay, and we will just do a basic recap that these ideal flows were essentially inviscid flows without vorticity, okay, and we got to this whole discussion of inviscid flows when we looked at our dimensionless Navier-Stokes equation, and we said that this RE is much greater than 1. So, 1 by RE, which is some epsilon, it is much less than 1. Let us not write it like epsilon, it is much less than 1. So, I am going to just drop this out naively and ignore any viscous effects. Okay. If you go back one lecture from here, you will recall that we had taken a governing equation, an ODE of this type. What was it? Something like this, I suppose. Can you go back in your notes? I don't remember. Was there a y here or a 1 here? Huh? There was a y here. Okay. So, we had looked at a governing ODE like this. We said that u of 0 is 0, u of 1 is 1. And we said that dropping this epsilon naively gives you only an outer solution, which is what these guys are, the ideal flows that we have discussed. When you do a, so let us say you write y as some epsilon c, which is the rescaled coordinate, then you can formulate an equation in c instead of y, and then what did we get? We will get d2u over dc square plus du by dc plus epsilon square c equals 0. After rescaling the coordinate, now we can drop this epsilon naively, and basically when we do this dropping of epsilon terms, we are evaluating things to leading order. Okay, that should be very clear to you by now, that this dropping out of epsilon terms from governing equations means we are basically computing the solution to leading order. Okay. So, now when we drop this out and calculate the solution, we get what is known as the inner solution. And to get the inner solution from our Navier-Stokes equations, we have to find a way to rescale our coordinate. Okay. We have to find a way to rescale our coordinate, and that brings us to the beginning of the boundary layer theory. Why boundary layer theory is important? As we saw in this flow past a wavy wall, there will be no force on this wavy wall if you solve only the inviscid flow past this wavy wall. So, you are practically interested in forces past, in forces on the objects when flow is going past these objects. So, any practically relevant quantity, you cannot compute it very properly using inviscid analysis. The lift you can compute, but the drag you cannot, and in reality both are equally important. So, the lift you can compute, but drag you cannot, and to estimate a good value of the drag, we need to look at this inner solution, which brings us to boundary layer theory. It is, I mean, there are a lot of names to different theories that are given in fluid mechanics, but this is where theory ends. All of it after that is asymptotics. Okay. Derivation of Navier-Stokes was where theory ended. Okay. It is all mathematics and asymptotics after that. And boundary layer theory and inviscid solution, as we have seen, is two parts of an asymptotic problem, which is a singular asymptotic problem. And in this boundary layer theory, in this course, we are particularly going to look at laminar and steady boundary layers. Okay. So far in our analysis, we have never mathematically introduced this approximation. What do we mean by laminar analysis? Okay. What do we mean by finding laminar flow equations. Okay, we will see this as we go towards instability and turbulence, that all of the solutions that we have been doing are laminar solutions, because there are particular characteristics of a turbulent flow which we have been ignoring altogether so far. Okay, there is no definition of turbulence. There are some characteristics which, if you find in a flow, it is safe to assume that the flow is turbulent, and we have been totally ignoring those characteristics. Yet we have been finding the solutions of these governing equations, which should tell you that it's a nonlinearity of the governing equation which basically admits multiple solutions, and some class of those solutions are laminar, the other are turbulent. Remember, Navier-Stokes are nonlinear equations. Okay, these are nonlinear PDEs. We don't even know how many solutions exist for these. There is no general theory of nonlinear PDEs. Okay, for algebraic equation you can say it's a second order nonlinearity, so two solutions will exist. We don't even know how many solutions will exist for a Navier-Stokes equation. Okay, so if you have been finding a solution, that is not the solution. We have been finding laminar flow solutions, but with the same boundary conditions, same initial conditions, you can find other solutions also. And there's that particular class of those solutions which obey some particular traits, we'll say those are not laminar, but those are turbulent solutions. So far this is something that you can qualitatively remember, but we have never introduced this mathematically in any approximation. Steady, we know, we ignore the unsteady term in the governing equation. Okay, we know uniformity, we ignore, let's say if it's uniform in x, we ignore del by del x terms in the governing equation, but we don't know what to do when you say okay, so as you solve assuming laminar solution. Okay, so you can just qualitatively remember this, and after we have done instability, it will become clear to you that all solutions basically that we have found, why are they laminar? Okay. So we are going to look at essentially laminar steady boundary layers, and the idea is now to find how to rescale this coordinate. Okay, to find how to rescale the coordinate, and I am going to leave you today by just this picture of a boundary layer where you have a flow of velocity u infinity in x direction, and let us say the pressure is also there P infinity, and there is a flat plate that starts at x equal to 0, and the flat plate is at y equal to 0. What you will see is that very close to this flat plate, or what is this x equal to 0 point, there is a layer that develops, outside which you have an outer solution which can be which you can approximate, and inside this there is an inner solution that is required, and the characteristic thickness of this layer we will call it as delta. Okay, so basically delta is your y direction length scale, and your x direction length scale will be this guy, which we will call as L. Okay, and we will divide our region into 4 smaller regions, where this guy is where L is similar to delta. This guy is where, let us say, delta is much larger than L. This region is again L similar to delta, and this region is where delta is much less than L. Okay, and we will soon see that all of the boundary layer theory discussion applies to this region. Okay, we do not rescale both x and y coordinates. Here it was an ODE, so there was no choice to make. This is a PD in x and y. So there is a choice to make. Which coordinate do you rescale? So x and y, you can think of them generally as, do we scale the streamwise coordinate, or do we scale the wall normal coordinate? Okay, this is how usually they will be called, because boundary layer theory can be applied to curved walls as well. Okay, so the general notion of streamwise and wall normal can be applied to curved walls. Okay, the x and y does not translate to your curved walls, right, but streamwise and wall normal names will translate to curved wall cases as well. So what we will do is we will take y as y length scale as delta, x length scale as L, and this should be very familiar to you guys. We did something very similar in lubrication approximation. Okay, we did something very similar in lubrication approximation where our y length scale was different than the x length scale. Okay, and we will again look at y star, which is y by delta, and x star, which is x by L, and carry on with our analysis. Okay. So you can come to my office tomorrow for looking at your